Now we're given these complex numbers w and z, and also u and v in terms of w and z. And we're told to prove that w and z are real if and only if u and v are real and u squared is less than or equal to 2v. Note that one side of this double logical implication has two components to it, the first being that u and v are real, and the second that u squared is less than or equal to 2v. And these must come together. In other words, they must both be shown to be implications of w and z being real, and in the other direction they must both be assumed. And the idea is then to show that both of them together imply that w and z are real. So it might help to think of this as three proofs. On the one hand, we have a single premise leading to two conclusions that must both be shown to be necessary implications of the premise. And on the other hand, we have a double premise leading to a single conclusion. And the most obvious of the three is that if w and z are real, then their sum and the sum of their squares are both going to be real. So w and z being real implies that u and v are real. Now, before doing what I did here and rushing into doing the first thing that comes to mind, think about what we have here. Two equations, one of them with quadratic terms, and an inequality that can be seen to depend on or to determine whether the numbers are real. If you just want to see the optimal way to do this question, skip to 3 minutes 40 now. Otherwise, I'll try to explain what I did. Firstly, to get this direction done with, which is the only if direction, it just remains to show that this inequality follows from w and z being real. One way to do this is just to consider what the inequality will look like in terms of w and z. So we'll have w plus z all squared on the left hand side, and 2w squared plus 2z squared on the right hand side. So taking that all over to the right hand side, we'll have another perfect square. So this argument begins by noting that a further implication of w and z being real is that w minus z is real, and then works back through those stages to the inequality. Now, going back the other way, we have to prove that if u and v are real and the inequality holds, then w and z are real. But the first way I thought of to do this is to let w and z be general complex numbers, and then to try to show that the premises imply that their imaginary parts must be 0. So we're assuming that u, which is equal to w plus z, is real, and writing that in terms of its components, we must have that the imaginary component, b plus d, is equal to 0. So z can then be expressed in terms of c and b only, and that then makes the next step slightly easier when we come to considering the consequences of v being real. So v being real implies that w squared plus z squared is real, and that implies that this expression in terms of a, b and c now must have an imaginary part equal to 0. So we get that 2b times a minus c is equal to 0. There are two possible cases here. In the case b is equal to 0, then we're done, because the imaginary parts of w and z are both 0, and so both are real. In the second case, a is equal to c, so the real parts of w and z are the same. In that case, we have a complex conjugate pair. Then arguing from the other premise, which is the inequality, with the numbers in this form, it can be shown that b must be equal to 0. So that method seems to work, but it took almost twice as long as the optimal method, which is to notice that working from the definitions of u and v and substituting one into the other gives a quadratic equation in w or in z, and then arguing from the discriminant, which consists of real numbers, importantly, because if it didn't, then we wouldn't be able to conclude that it was non-negative. We see that the other premise shows that it is in fact non-negative, and so we can conclude that w is real. Then we can argue that because the equations are symmetric in w and z, the choice to make this argument in w rather than z was arbitrary, and so it holds for z as well, and so z is real. And actually the really nice thing about this method is that it takes care of the proof in the other direction as well. Because we have a quadratic, of which the roots are w and z, and since we're arguing from the fact that w and z are real, it must have a non-negative discriminant, so that gives the inequality, and then it just remains to show that u and v are real, which, as we saw earlier, is straightforward. One thing to take away from this is, if you're ever unsure whether what you're planning to do is what the question setter intended, then taking a couple of minutes to look for a better alternative can be very worthwhile. So for part 2 then, we have a system of equations and we're looking for possible values of u. One thing to notice here is that the way this question is written hints at defining a further number v as u squared minus 2/3. Now, as far as I'm aware, there's never been a step question structured in a way that's so suggestive of a definition, only for it then to prove that making the definition actually inhibits progress. And it's far worse to miss a connection between parts of a question than it is to have a redundant line in an argument, so I'm going to go ahead and make the definition. So, as usual with simultaneous systems of equations, we're hoping to get an equation just in the terms that we're interested in, which in this case is u and lambda, and we can do that by using the sum of two cubes identity in the third equation, and then substituting in values for w plus z and w squared plus z squared from the first and second equations. We'll just need to manufacture a wz term, which we can do by squaring the first equation and using the second equation to write the result in terms of u. And so we get that wz is equal to 1/3. So now we have everything we need to write this sum of two cubes identity in terms of u only. So doing so, and then equating it to the right hand side of the third equation, we get this. And the subsequent lines there are just the usual way of solving a cubic, by spotting that one is a root. So rest assured that there are three possible values of u, all real. And that's what we have here, because one's obviously real, and we're given that lambda is positive, which implies that that discriminant is positive, which implies that the quadratic has two distinct real roots. We're also asked to show that for some particular value of lambda, there's an exception to there being three possible values for u. And that value of lambda then must be the one that gives a solution for the quadratic that's equal to the solution that we already have, which is 1. So, yes, we'd still have three roots, but two of them would have the same value, so there'd only be two possible values of u. Finally, we're asked, are w and z necessarily real? Give a proof or counterexample. It'd be nice if they weren't and we could find a counterexample, because that's usually the easier of the two options. So thinking back to part 1, we know that for any complex numbers, w, z, u and v, as defined, w and z are only real if u and v are real, and u squared is less than or equal to 2v. So we can check those conditions. We've just shown that u is real, and so v, as we defined it, is also real. And so the reality of w and z just comes down to the inequality. And whether or not the inequality holds is equivalent to asking whether this expression is positive or non-negative. And it is in the case that, and only in the case that, u squared is greater than or equal to 4/3. So we can use this to make a solid argument for the counterexample. We can argue that by part 1, w and z are real only if u squared is less than or equal to 2v, and therefore an obvious counterexample would be the case u is equal to 1. And that would seem to be a sufficient proof that u equals 1 is a counterexample, but in the examiner's report it says counterexamples were not always shown to be counterexamples, and the method used in the official solutions is not to bother referring to part 1 at all, but just to test the counterexample directly in the equations and show that way that it's a counterexample. Now, generally it's necessary to test counterexamples in the equations, but the whole arc of this question has been towards showing that if a given counterexample satisfies certain conditions, then it absolutely is a counterexample. And so this would seem to be an exception, but then again they make the rules, so perhaps to be on the safe side, test counterexamples unless told explicitly not to do.